Welcome to the course on two-dimensional signal processing, principles and practices. We'll do the implementation of the KL transform and the Hadamard transform. Hadamard transform we had seen already with the examples in the previous lectures. So we would look at the Hadamard transform and then move on to the KL transform and its implementation, both of them. So we had seen this, what is the Hadamard matrix and what is the side of 2 power n, which is meaning of this instead of a size in the Hadamard transform, and which is h naught is 1 and h1 is 1 1 1 minus 1. So it would contain only the 1 and minus 1 values in the kernels, and h2 can be obtained from Kronecker product of h1 and h1 to get h2, so which is nothing but this. Similarly, it will proceed for the different kernels. So this is the kernel size of 4 by 4 and 2 by 2 here. So this can be extended to different sides as well. So using this Hadamard transform for an n by n matrix of x. So how do we get the transform is 1 by n hx h transpose, where it is also h is equal to h transpose here. So it is valid 1 by n hx h, and the inverse can be obtained from this x 1 by n h v, as we know v and x can be obtained. This is the inverse transform. So we had seen in the previous lecture. So just to recall this and the example what we had done with it, x is 2 3 4 2, and for this implementation we in the code we write it x is 2 3 and 4 2, that and fix the size of x, which is the n, and then get the Hadamard matrix, that is the square root of n is used. The Hadamard is again the built-in function here, the Hadamard of n to get h. So yeah, if you fix n depends on x size, n would be fixed for it, and then to get the transform, Hadamard transform. So it's a square root of n gives the normalized one Hadamard here, and getting the transform, we are f is here h into x h dash h transpose h x h transpose is the transformed x, which is f here. So the Hadamard coefficients we get it here, and this Hadamard coefficients can be displayed in the kernel in the command window, where this you get the with the images of like an image to plot it. This one we use this p and q for the changing like the horizontal and vertical one. So get h and h dash, which is the transpose. So this is the outer product, in which the same thing which for the section image section B as well. So you use the color map and access properties and what are the Hadamard basis images with the coefficient. So this Hadamard coefficients what we obtained for this 5.5 minus 5 minus 0.5 minus 1.5, and now the basis images are h of 0, 0, 0, 1, 1, 0, 1, 1. So you can see 1 and minus 1, and the basis images, just this is plotted in the grayscale as a image, these basis images. So once we have this basis images and we can using the coefficients, we can get back the sequence as well. So from these are the coefficients as well, and basis images obtained through this code, where you can see h and h transpose outer product gives this basis images 0 0 0 1 1 0 1 1. So from that, if you take an example 2 of this Hadamard transform, and with x is 4 by 4 now. So if it's increasing, what is the kernel we need to have for getting the Hadamard transform of this x? What we said is h1 Kronecker product h1. Okay, so then to obtain h2, like so x is this values 1 2 3 4 random numbers are taken here. It's not belonging to any of the particular image. So but we would like to show the outputs as images and the basis images as well. So the size of x is to be noted, and Hadamard similarly, what Hadamard n square root of n, the matrix, and get the coefficients or the transformed x. F is equal to h x h dash, which is the transpose, x is the image size 4 here, and with the Hadamard kernel. Okay, so actually we use it to get it in the transform domain, either in the DCT or the DFT or Hadamard transform or DST. We use a kernel, so those kernels are fixed in case of these transforms. Like the Hadamard, the 4 is the number what is in the kernel is fixed for 4, and that is So in the DFT, it comes from the twiddle factor matrix. So that is for 4 or 2 or 3, depends on n, it is fixed. Similarly, in DCT as well as this DST as well. And then, so these are in these transforms, this matrix, twiddle factor matrix especially, is called this kernel, the Hadamard kernel or the DST kernel, DCT kernel or DFT kernel. So now from those kernel we can obtain using the x here and get the transformed coefficients. So f is here, it is plotted as image here. So that's how it is. P and Q are again the rows and columns to get it. The basis images, to obtain the basis images H and P and Q are used. Take the image section. So the color map used is gray. You can note down in all the cases. And we have the coefficients which is plotted. It depends on the DD, this 2D Hadamard coefficient. So what we got is the coefficient 4 by 4. So the Hadamard kernel is of 4 by 4, and H, that Hadamard kernel, into X into H transpose gives this 2D Hadamard coefficients. And these are the basis images which are obtained for these using the kernels. Okay, so you can see the horizontal stripes and then vertical stripes ourselves. If both of them are there, you can see again here the combination of this is shown in the diagonal as well as in these values as well. Okay, so here, and this, it should be read row wise and column wise, or one particular value, and this combination is here. So this combination is here, this combination is over here. So we can plot like K1 and K2 be varied in the case. So it is in the number n is varied in this Hadamard transform. So the basis images are these things. Now the basis images as well as the Hadamard coefficients are 1 and minus 1 are shown over here, and this is 1 and 1 1 1 and 4 by 4. So we have got this by multiplying. The kernel is obtained, if you recall, in this case the kernel which is obtained here in the Hadamard transform with the multiplication, the one which here, 1 1. So in the product we get this H1 1 with this one element with all the H1 and one element. That's why we get it here, this one, if you recall. And similarly this 1 is multiplied with that H1 of that whole, get this another 4 elements, and 1 is again getting this H2. So minus 1. So all the components of this elements will be minus 1 and this becomes 1. So this is how it is getting extended, so 1 to 1. So similarly in the case of basis images as well, we got it in the same thing in the this is called the kernel. This is called the kernel. So similarly in the DFT and DCT to obtain the transforms. Now coming back to the Hadamard this example, what we got. So these are the basis images. For the second example, it took the 4 by 4 X and its image we have obtained the basis images. So the basis images of 2 by 2 and basis images for the 4 by 4 are shown over here. And these are the coefficients what we have got through this. Now for DCT, DFT and DST and an image. So if you apply those things on an image, so what should be the outcome of the image or the transformed image? So we take this image which is given as a window image we can take. So we can read this image and fix the size of it. Either it can be of 256 or this 8 by 8 or the 128 by 128 and so on. So it depends on the number of pixels we take it, and then convert this only the color image into gray. So for processing here, so this is RGB to gray. It's a built-in function which is applied on the image. IMRead is the reading the window.jpg image and getting this. For that, double values or IM2 double values are fixed here. After that you fix the size of this image. So apply the DCT2 to get the DCT of coefficients of that image, and IDCT2. So on the DCT, so the coefficients on that, if I apply inverse DCT, get the image back. And here it is only real coefficients, so there is no need to go for the absolute or the phase information here. But in the case of DFT, if you apply the DFT to image, then IFFT2 by, this is a complex number, so then IFT2 to DFT, so you can fix the size n by n as well and give it, because I is already fixed size, so we didn't give this n by n, n cross n. We can give this for FFT2 n cross n as well, and use this in the IFT2. This is inverse DFT. From the coefficients we can get back this image here. So this is complex coefficient, and this complex coefficient is just used here for the inverse. Supposing we plot it for the magnitude alone, so this complex coefficient is made as absolute 1 and then the phase. So now for this is for the DCT and this is for the DFT case. So DCT and DFT on applying on the image, whereas in the case of DST, that is discrete sign transform, the kernel matrix n, so we can use the DST as well. So the function is made for obtaining the DST. Zeros of n by n, n cross n, and k is varying from the 1 to n. So for n is in the equation, n and k are the same meaning as in the equation, and write it, the kernel matrix is here is square root of root 2 by n plus 1 and sine pi k n by n plus 1. So this is k plus 1 and n plus 1. So here k is already varying from 1 to n values, so it is not made as k plus 1 and n plus 1. So it's just taken as k and n. So this is the value DST matrix M. So getting the DST matrix, this is going to be the M, values of m and n. So DST matrix is nothing but the obtaining the kernel for this case. This is the DST matrix function which we have used here. So this nothing but getting the total factor matrix as we have in the kernel of the DFT. So this is in the DST case. So once have this matrices, yes, as we have denoted as yes in the previous cases, yes star I is or Sn dash. This is the transpose getting the DST coefficient of the image. So this kernel is formed using the basis function which is used in the DST. So this is one way to do it, and in the other case the DCT and the DFT you have already the transforms directly, or the kernel matrix can be obtained and then use this function to get the matrix as well, the coefficients. So similarly the inverse transform is Sm dash is DST Sn. This is to just make the transforms sizes equal. So we have done the dash and DST Sn. So this is getting back the image here. So this here we had plotted only the magnitudes and the image background. So this is to show that matrix to gray of the DCT magnitude and the DFT magnitude plot, and also the DST magnitude plot. So for that we can have the 2D DCT magnitude, and it doesn't show much. You can see the variations over here, very little variations. Also the DFT magnitude, you can see that, and the magnitude details minus pi to plus pi and the center. So you can see the variation of these variations. That slight variations show the frequency change in the horizontal direction, vertical direction, and the diagonal as well. So we can clearly observe that with when we do the images and its processing of the DFT and taking the frequency component and all those things, and we would interpret the meaning of these things, the frequency varying in horizontal direction, frequency varying in vertical direction, and diagonally if they are varying, so that those can be identified from the magnitude plot of the DFT. Also the case of this 2D DST, so it shows the small variations here. Here's not much information from the DST magnitude as well, but this DFT magnitude, you can see the changes in frequency. Where the image which we had taken here, have the example image which has the horizontal lines, you can see, and there are these are major horizontal lines and some vertical lines as well. So these variations could be very easily the frequency variations, that high frequency components are visible in case of DFT. The interpretation can be done as when we do this with the image processing, that variation in horizontal, this is with that, and then here is a vertical one, horizontal one, and then diagonal variations of the frequencies can be seen in the DFT plot. So now how do we get this using this magnitude and the phase plot? DFT will also have the phase plot, which is not shown over here. We could not get much from the phase plot, but how phase plot is important in this case, we would see that when we do the reconstruction of these images from the DFT magnitude and phase plot. What is the meaning of how the phase plot is very much important in that case? So we can now just taking the reconstruction process of the images, what we had, the image and its magnitude plot is known. So from the to plot this reconstructed image, that is having this use this IMShow to show the image. That's a command used to show the image, and IMShow, these are the variables which have obtained from the inverse transform, if you recall from the DCT REC reconstruction, and showing that this is 2D DCT reconstructed, and similarly this is the reconstructed from the 2D DFT and 2D this is DST reconstructed one. So from that, so you can say this is the original image and the reconstructed from 2D DCT. So the coefficients, from that coefficients we have got some most of them are in the low frequency region, the coefficients. So we have just used it, we have not removed any coefficients. For this reconstruction we have just used it. We have shown in 1D case that 1D DCT that if you remove some of the coefficients, the energy compaction property, which is on the low frequency region, how we can efficiently reconstruct. There will be small error in that reconstruction, but we have not studied that now in the 2D, but it is just to show that how do we get this reconstructed image. So this is a 2D DCT reconstructed with using all the coefficients. Similarly 2D DFT using all the coefficients. So the magnitude plot, and there is a phase plot, the phase information. So the magnitude and phase information is used to reconstruct it. So here, so this is the reconstructed 2D DFT and reconstructed 2D DST. So there are different. So these are all used in this DCT and DST and Hadamard transforms. Hadamard is also further used in case of a few other applications, but for the energy compaction property. So DCT is preferred in the image compression. Also this DST also uses the energy good. It also gives the good energy compaction property. So this is to show that same image which can be obtained from the coefficients or the transform domain, we can get back this reconstructed using this. So the details of it, what are the information when we get it through this, especially the frequency component, high frequency and low frequency components, the edges, lines and other things, all of them are the frequency components in the case of an image. So how do we get one by one? What is the relation between this bin indices and these frequency informations? So if you vary the bin indices, what are the information it can give? So these details we'll study in the later section with the analysis of the images. So this part is just to show that whatever the transforms we had learned, and those transforms can be applied to change the image into transform domain and from transform domain to image. So now coming to this Karhunen law transform, that is a KL transform, so which is little different from the transforms what we had learned. So this is introduced as a series expansion of random processes, especially this KL transform, and it is equivalent to, or it is same as this principal component analysis. What does it do and what this transform implies, and what is the meaning of this KL transform to images, and how do we apply them? So these things we'll learn. So it's called this also as because it is similar to the principal component analysis, it is also called principal component transform, and this also called eigenvector transform. The another name of it is eigenvector, and it is based on the eigenvectors of the autocorrelation matrix of the input sequence. So first we need to know this input sequence and its autocorrelation matrix and the eigenvalue eigenvectors, how these are related. Okay, so now we take this, if x is the input vector, and then of n cross a, and lambda k and phi k. These two are the kth eigenvalue and corresponding eigenvectors of R. So take x and find out its autocorrelation matrix R XX transpose, and then find the lambda and phi, that is eigenvalue and eigenvectors of corresponding eigenvalues of this autocorrelation matrix. Okay, then R is autocorrelation matrix into phi k, which is the eigenvector, equal to lambda phi k. So this is lambda is the eigenvalue. So like Ax equal to lambda x. So you have this x's, that is the eigenvector of R. So which is valid for the k varying from 1 to n. Okay, so this is the KL transform. If this is these are the conditions. So you know x, you know autocorrelation matrix of x, and that phi is the eigenvector of the corresponding eigenvalues. Then the KL transform is V equal to psi dagger x, where psi is formed from the columns of phi k, that is the autocorrelation matrix of x of eigenvectors. It is corresponding to the eigenvalues what we obtained here. So using this phi k, this psi, the columns of psi dagger is formed. This is dagger implies this complex conjugate transpose. Here it's real, so we use this psi transpose usually in the transforms. So the psi is formed with a column of phi k. So psi and R is the autocorrelation matrix psi. So it's a dagger. It is diagonalizable, unitarily diagonalizable. That is lambda is having the lambda 1 to lambda n. So let's see this. What is the use of all these things? So like R is unitarily diagonalizable by the matrix of its eigenvectors. So if we say that, if we take this as a principal component, and what is the relation between this, how is it can be done, feature descriptor. So taking an input sample which is represented by vector x, and it's as a KL transform is, as I said, it is psi transpose x, or the dagger. We can use alternatively this sign. So the elements of V or KL transform coefficients are the principal components. This itself is called this principal component of x, and this KL transform, it can be diagonalizable with the autocorrelation matrix lambda 1, lambda 2, arranged in the diagonalizable form. So these coefficients which we get, transform coefficients, are uncorrelated. We are going to see through the example, and the first few coefficients of V, this one, the transform coefficients, contain the most important information, and these are used for this feature descriptors of the image. But if we take them as this image data of each location and represented by a vector x, okay, so this is the image data, that is x. Okay, so then in this, applying KL, so gets the V, and this V corresponds to one transform feature. So which is actually how this transform, as we said, that it is going to be the first few coefficients of V are having get the V for x using the psi, but this V is having the few coefficients and get it in the descending order, and arrange in the image form, that image transform vectors. And if you see this, those are nothing but the principal components of the image. Each V can have form an image. So that's called the principal component image, and for the second, third, remaining coefficients also form a principal component of the image. So the first one is the important. So this is for lambda 1 greater than lambda 2 and lambda n. So the lambda 1 will be the highest. So get the lambda, those are eigenvalues of R, that is the autocorrelation matrix, and arrange it in the descending order. So this one has the first principal component image contains the maximum average energy. So this will have less, and this will have less, and so on. So progressively it will have the lesser and lesser energy, where the very first one will have the more average energy. So in the reconstruction process, if we have this V coefficients, what we have done, that coefficients, can we use all of them, or this most of the energy are not in the related coefficients. So these are in the first few coefficients only. So it is the energy is packed in that first few coefficients. So if V is V1, V2, Vn, then we can reduce this by V1, V2 to Vk, and remaining 0. So form this Vk, which is having the first principal components are the transform coefficients which have this energy. So xk can be obtained from the psi Vk. So the Vk is only having the partial V1 to Vk, remaining or made 0. So smaller the k, If the k value is smaller, that means it gives the compression. That's obvious. We use this. If this k value is larger, better reconstruction. It's obvious. If you use all the coefficients, then you will get x back as a better image. So one more thing is that here the kernel matrix, the psi, is not a constant for the size of the image or the input x, like in other transforms. It varies, depends on, because this eigenvalue and eigenvectors are involved in forming the kernel of the KL transform. So in this way, the KL transform is different from DFT, DCT and DST, as well as Hadamard. So the dominant components here, we need to only preserve the most significant information, then the rest of them are not. Rest of them are made 0. So for an example, we take x1 and x2. The two, consider this 2 by 1 random vector, in which this is x1 and x2. These are two realizations of equal probability, because this KL transform is based on the random processes. So k1 and k2 having these two elements are the two realizations. We can take this x1 and x2 or name it in any way. So find this KL transform of it. So x1 and x2, take it as them, and the autocorrelation matrix. First thing is x transpose. We find the x transpose for both of them, and we 1 by 2 find the autocorrelation matrix and find the eigenvalues of autocorrelation matrix, that is lambda, and then sort this lambda in the descending order. That means first lambda, the highest value, and then next one, and so on. So this sort function is used. And then you can collect this IDX as V, and then take the diagonal values only. So here diagonal of D, this is 1. So after making that resizing, and this stage is the important one, the psi is equal to V. So psi matrix, what is the kernel, is the V, nothing but the V what we obtained from here. So this is V of the lambda which we got, and then the eigenvectors after and getting the KL transform. KL transform for psi dash x1 and psi dash x2. So the two matrices x1 and x2 get v1 and v2 separately. So this we can plot all of them, or they get these displays done over it. So this is the way in which it is done for the transform. So just get V in terms of psi transpose x. That's the transformed coefficients of the KL. So we can get what are the printed ones. We can say here is the autocorrelation matrix for the one example, and the eigenvalues are obtained for this, and then eigenvectors for that, and then columns of this eigenvectors are arranged to get the eigenvector. For this eigenvalue, one eigenvector, and for the other eigenvalue get the other eigenvector, and arrange it as a columns of this eigenvector. This is nothing but psi. So this transform is psi transpose and in the x, right? So psi transpose x, you directly do it, you would get it, or x1, for x1 the transform is this, x2 this is the transform. So what we get is x1 and x2 are the transformed matrices of the KL transform matrices. So if we take this transform matrices V1 transpose, V2 transpose, find the autocorrelation of the coefficients what we got through this transform, and you can get back the lambda 1 and lambda 2. This is the one which we obtained here. So these are uncorrelated. That's what we're trying to say. This is KL transform. Transform coefficients are uncorrelated. So you can see them, lambda 1 and lambda 2 separately, and the variance of these transform coefficients are equal to the R, which is the autocorrelation function itself here of the transform. So the one thing to be noted here is this: the kernel is different for different input images, the KL transform. In that way it differs from the other transforms. So for the example of 2, in which 4, 3, minus 1 and 6. So if you take the another example x, in which, so you find the autocorrelation matrix x, because in the previous example it is given 2x, to x1 and x2 separately be found, or make it as a column and found. So here is only one column of x. Okay, so suppose a strip of the image strip, one column, then find the autocorrelation of that, and then eigenvalues, also take the eigenvalues, sort it out, and find the eigenvectors, also rearrange them here in the diagonal, and get the transforms like This is to get the non-zero entries of the eigenvector. So in the eigenvectors, you can have the negative values as a first element, or some non-zero values to be taken to be in the eigenvector. So for that, we have done the corrections here. You may follow that it is with the 1 e power minus 10. So the transform is psi transpose x is the KL transform, which is obtained here, psi transpose x, and this is to avoid the negatives in the eigenvectors and display the coefficients and eigenvalues and so on. So what we have this, the autocorrelation matrix and its eigenvalues. You can see 62000, and the basis vectors are eigenvectors. You can see that this for 4×4 it is different. Even for any 4×4 image, it depends on the image values and its autocorrelation matrix. So the kernel is different here, and these are the KL transform coefficient is this. From this coefficient, we can obtain the remaining, how it is uncorrelated can also be proved. VV transpose, take the autocorrelation function of it, it would give us back the eigenvalues. So with this, we have seen the KL transform and how it is different from the other transform, and we use this relating this with the principal component analysis. This is very much used in the energy compaction property, because all of the energies are lying in the initial portion of the coefficients. So those coefficients can be used for a reconstruction process. Theoretically, yes, it can be, the reconstruction is possible with the coefficients, and we have to identify each principal component which is associated with the eigenvalue of the autocorrelation matrix of the image. So in that way, these kernels can be formed, and we have seen this kernels also is a different, it's not constant, like it is not fixed like in the other transforms. So this transform is especially used in the energy compaction property as well. So this is one of the transforms used like DCT and DST in the images, and we'll further explore these transforms. How do we use it in the image processing, and to extract the features of the image, and the particular features, the basic features of the image, how do we extract them. Also, we would analyze these images using these transforms, DFT, DCT and DST and Hadamard transforms as well. With this, we would be completing all the transforms, and how do we implement them using this MATLAB. We will use this transforms also for the images in case of real-time capturing of 2D sequences, that is images, and applying to them, and how to deploy these things in the compact trio for real-time image processing. We'll see them in the lab demos, and how do we use this transforms for the real-time captured images. So we will continue with the Z transform in the next lecture. Thank you.